In this final video, we are going to take a look at a rather unexpected and little known application of state machine in combinatorics. The method is called the transfer matrix method. To understand this, let's consider this simple example first. Here I have shown you some airlines. So these are different cities, some airports, A1, A2, A3, B1, B2 and C1 to C4, and these arrows show the airlines connecting them. Suppose I ask you the question, how many routes are there that go from A3 to C4? Now how do you compute them? You can go like this, A3 to B2, then to C4, or A3 to B1, either using this path or using that path, and then from B1 to C4 there are three different paths. So if you compute them, you will see that you are doing this computation 2. So if you make the stopover at B1, then there are 2 ways to get to B1, and then there are 3 ways to get from B1 to C4. So 2 times 3 plus you can make the stopover at B2. So it will be 1 times 1. The answer will be 7. Now you may not really feel it, but actually you are doing one entry of a matrix multiplication like this. So here for the first part, for all the airlines from A's to the B's, you have this matrix. These are what are called transfer matrices. And similarly from the B's to C's, you have another matrix. Here I have this red 2, means from A3 there are 2 routes to B1. Similarly from A1 I have 1 route to B2, so this number is 1. Similarly for this, and what we are actually doing is we are basically multiplying these two matrices. And this 7 is exactly what we obtained earlier, and this computation is essentially what we are doing when we are computing this 7. So I can reduce this combinatorial problem to a matrix multiplication problem. Now let us see when we are working with the same set. So earlier we had the A's, from that we went to the B's, from there we went to the C's, but here I have only P1, P2, P3, and here are the airlines that are connecting them together. Here also you can think of a transfer matrix which will be a square. Like this, P1 to P1 there is only 1, that is a self loop. Then P2 to P2 0, because there is no loop from P2 to P2. P3 to, say P1 to P3 we have 2, because from P1 to P3 there are 2 arrows that are leading. Now if I ask yourself some question, you can answer them based on this matrix. So let's give it a name A. Now if I compute A square, what does that tell me? If I compute A square, I get 2, 1, 6, 1, 1, 2, etc. What this really tells me is in how many ways I can get from one place to another using exactly 2 arrows. For instance, here I have got a 2. What it says is from P2 to P3, there are exactly 2 paths of length 2, P2 to P3. One path is this, P1 to following this arrow, then this arrow. The other is this arrow, then following this arrow. In general, the ijth entry of a to the power k gives the number of paths of length k from pi to pj. So this so far does not involve any finite automaton, but this is going to be very crucial. Now we are going to apply this using finite state machine. Here is a little counting problem. I have made this problem look as weird as possible. It is not one of the regular type problem. I want to count the number, let's call it Bn, of sequences of squares, red, green and blue squares. Total number of squares must be n and must have 2 consecutive reds somewhere before 3 consecutive blues. So we want to count some strings of squares of length n satisfying this property. So let's take some examples. So all these things are good. So they satisfy this condition. So somewhere we have 2 red squares consecutive before 3 consecutive blues. Here again we have 2 consecutive red before 3 consecutive blues. In this case we do not have that property because I do not see any 3 consecutive blues here. Here we do have 3 consecutive blues but we do not have 2 consecutive reds. Here we do have 3 consecutive blues and 2 consecutive reds but they occur in the opposite order. So we want to count all such things, all the good things for any given n. Now you may think for some time and convince yourself that there does not seem to be any straightforward way of solving it. Now we are going to demonstrate how to apply state machine to solve this problem. So first you have to create a state machine which will recognize this pattern. So it goes like this. So you first start with start, that's the start state, and your final aim is to reach this particular configuration, 2 reds somewhere before 3 blues, and this little space says that you may have anything in between. So we are basically building it up. First you say 1 red, then another red immediately after that, then possibly after some gap a blue, then 2 blues, and then 3 blues. Now we will connect them with various arrows and create the finite automaton. So first you just put all the obvious arrows, the so-called success arrows. From start, the moment you get a red square, so your inputs are the red squares and the blue squares, you come to this. You get another red square, then you are in this state, you have seen 2 consecutive red square. Then you get a blue square, you get red, red, then blue, another blue, red, red, blue, blue, yet another blue, red, red, blue, 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 and you have reached your holy grail. Okay, now let's take a look at the failure arrows. Suppose at the very beginning you do not get a red square, you get either blue or green, in which case you continue to wait. So you have 2 self loops here, one for green and the other for blue. Now suppose you have come to this red and then immediately after that, instead of getting another red, you get a blue or green, which means the first red that you got really is not starting the pattern because it is immediately followed by some blue or green, so you get back to your original start state. Here also we have got 2 arrows, one labeled green, the other labeled blue. In this way we can fill in all the other failure arrows. So whenever you are not getting what you want in order to move forward, you have to go back appropriately. And at the very end, we have to, so since we have succeeded, now we have all the 3 arrows leading to this, meaning that we have already achieved whatever pattern we wanted to achieve. So this little state machine will recognize our pattern. So if keep on feeding it, the squares one by one, if you do have the pattern, you are going to arrive at this particular state. So now the question becomes, in exactly how many ways can you reach state 6, I have just numbered them as 1, 2, 3, 4, 5, 6, from 1 using a path of length exactly n. So your original problem now reduces to finding paths of a given length. Well, what do? I just create the transfer matrix for that. So I create the transfer matrix just by looking at it. Let's quickly see. From 1 to 1, I have 2 self loops since I have this thing. Similarly, I have this 3 which says from 6 to 6 you have 3 self loops, and from 2 you can go to 3 in only one way, from 2 I can go to 3 in only one way, like this. So I just immediately write down this transfer matrix. And then what do? I have to find out a to the power n and look at the 1/6 entry. Starting from 1 ending to 6 will give me the number of such patterns of length n, that is precisely the Bn we are looking for. Now it might look like a formidable task to raise it to a high power, but we can use a computer. So you can either write your own program or use this symbolic computation system called Maxima, which is free to use. You can download it. And then I just entered a matrix. This is the syntax of Maxima, and then I just compute a to the power, say 45. I want to find all such patterns of length 45, and this turns out to be this huge matrix, of which I only care about the 1/6 entry, which I have shown here in larger font, and this is the exact number of strings of red, green and blue squares of length 45 satisfying that property. That's pretty impressive, right? It was very difficult to compute it in any other way. In fact, I do not know of any other way of computing it. And the method is extremely general. Okay, now you might think that that's good, but that's one uncomfortable fact. You just get a number. Can we not get some formula for Bn in terms of n? Well, this is a very general method, and in general, for a combinatorics problem, the answer may not be expressible as a simple function of n. So you are not getting any function. However, if you want to deal with Bn analytically, then this method also has got you covered, because it can provide you with the generating function of Bn's. So the generating function of Bn is what is called a formal power series, like this: b0 plus b1t plus b2t squared plus b3t cube, etc., which means you are just writing them as a sequence, and just to keep track of the position, you multiply this with the power of t. Now, what we are interested in is the 1/6 entry. So this thing is actually the 1/6 entry of I plus AT plus a squared t squared, etc., which is obvious because the 1/6 entry of A is B1, 1/6 entry of A squared is B2, and so on, and 1/6 entry of I, which is just 0 because I is identity matrix, that is B0, which anyway is 0. Okay, so you get this simple thing. Now, you can compute this quite easily because this happens to be I minus TA whole inverse. This is in keeping with our standard algebraic identity, 1 plus x squared is 1 by 1 minus x. Now you may feel a little uncomfortable because there we need a condition that absolute value of x should be less than 1. What happened to that condition here? Don't worry, because we are working with formal power series, we really do not need that condition. You can think about that, about why that is the case. I am not going to go into that into this video. Okay, so let's just try that out using our computing system. So I compute 1 minus TA using maxima, and this is the matrix. Then I compute its inverse and extract its 1/6 element, again using maxima. It turns out to be this: t to the power 5 divided by this. Now, this one is a nice polynomial. Downstairs and upstairs also we have a polynomial, t to the power 5. From this, you can immediately write down a generating function for Bn's. Now, how do I get from this to this? I will not tell you that. It's a simple exercise for you to ponder over. I will just give you a little hint. The hint is this: look at all the coefficients and observe that they occur in reverse order. Here you have minus 12, here this becomes plus 12. Minus 20, this becomes plus 20. Minus 10, plus 10, plus 6, minus 6, and so on. Just fiddle around with a little bit and you can immediately see that this gives rise to this generating function, which is a very useful tool in case you want to study these things analytically. Okay, that's the end of this playlist.